non-abelian. It comes in these two flavors. So that's like the gauge sector, and in addition to that, you have some matter on sites, which will usually be fermions transforming in some red R. And what makes it a gauge theory is that we have some local constraint, a Gauss law, which basically tells you that as you move from one link to the next, the electric field go up by however much charge was on that side. And in addition to that, we have some dynamics given by some Hamiltonian, which I've written schematically here. So there's gauge sector, which only has an electric field because I know Poincare operators in one dimension. And then there's also has a matter part, which can depend on what matter you put in. And also from the point of view of these networks, it's more standard than how you have to treat the gauge field. So the way you go about doing this usually is like in one of two ways broadly. So the first thing you can do, because we're in one dimension, is to basically just fully gauge fix and set all the U's to 1, which allows you to solve the Gauss law for the electric field. So basically you find that the electric field is going to be equal to the sum of charges that preceded it. And then the only thing that's left of this constraint is like a global constraint that says that the total charge has to be 0. There's also another scheme you could come up with where you try to keep all the states, so both the states corresponding to the gauge fields and the matter, and then you try to engineer your wave function ansatz such that it automatically solves Gauss law. And one like important difference between these two kind of approaches is that in the first one, when we have to compute this electric energy, then we infer it from the charges. So the L becomes, at least looks, non-local. While in the second approach, where you kind of just keep the state, then you can just read off what is the representation, what is the electric field, and just compute the electric field like that. Right. So this state, this is kind of just like quantum chain, and some very powerful methods for solving these kind of problems are matrix product state algorithms and like geometry and sorts. So we try to put in that framework, and people have done that to great effect. So for this first kind of setup where we full gauge fixed, we still had this extra constraint, this global constraint, but that's not really too complicated because this looks like going to a symmetry sector, have some global symmetry, and that's something that people in condensed matter has already thought about because they all like global symmetries. So there's this concept of a symmetric MPS, which is also sometimes called the quantum number conserving G, which just like takes us into the mix, and it's easy to impose that. So people have done this in a bunch of different papers, in particular, Grisham and operators have done this recently for Schlinger model. But yeah, one thing you could say that's not so nice about this approach is that the translational variance is sort of obscured because you have this thing that L is computed as a bunch of different Q's at different points. And that makes it hard to understand how you would generalize this to a suite of methods that exists for infinite system sizes where translation variance is important. In the other setup, then as said, then you have to come up with some ansatz that eventually solves the Gauss law, which means that you have to take some NPS ansatz, which is like somewhat non-standard. It's not just what we do if you were to solve some spin model, to be sure that the Gauss law is solved. And this actually makes it quite hard to do non-abelian gauge theories, which we would like to do. So that's like one drawback. Another drawback is that because you're keeping the gauge theory states as in your Hilbert space, your computer can only have so many states. So that means that the electric field, which can go to any value, you have to cut that off as some fixed cutoff and run with that in your simulation. So what I'm going to do in this talk is I'm going to argue for another point of view where we try to use the internal structure of the matrix product state to include the gauge field degrees of freedom. And I'll not just try to change the point of view, I will also like introduce some new technology, some new kind of matrix product operators that then will enable me to implement pretty general lattice gauge theories with this technology. And a few like nice points for this is that it's not going to be a big change to what these MPSs are. So it's easy to implement this into existing codes and use the normal algorithms. And another thing is that you don't have to commit at the beginning to a fixed cutoff for your electric field. The algorithm will sort of just do that dynamically. And then also it comes out to be translation invariant. So you can use these infinite system size algorithms, which has like its own set of advantages, for example, with boundary effects, and like you don't have to extrapolate to a large lattice if you are interested in continuum. Right. So this is kind of the overview, and to understand how this works, I'll have to tell you a little bit about multi-product states. So there are an ansatz for 1D quantum chains. So here I have some state, and these are the kets for local Hilbert spaces. And rather than having some generic wave function, I have this matrix product structure where I have an explicit index, which is contracted with a ket, and then I have like an implicit one that goes in the matrix multiplication. So you can make this kind of diagram where you have the APS tensor sitting here with the physical leg, which goes into the ket, and then you have the two virtual ones that contract with the neighboring tensor. And one way of understanding why you would want to work with these kind of objects is just count how many parameters you have. So if you say that this virtual index has a bond dimension of chi, then this tensor here will have like chi squared times d elements, where d is dimension of this Hilbert space down here. And then so for the whole chain, you would basically just get n times that number. So it's linear in the system size, whereas a generic state would be exponential in the system size. So of course, this cannot approximate any state, but it works well for gap ground states. Right. So when you can commit it to this kind of ansatz, then you can develop like whole calculus of how to do normal quantum mechanics operations. So you can do overlaps. You take a state and a conjugate and you click them together, and then you get this kind of tensor work that you need to evaluate. You can also take your state, act with an operator, and then project on some other state and make a matrix element. And this is how we get started with matrix product states.
I interrupt this.
Yeah.
It feels like this is a single particle ansatz, but I guess it's
No.
more general than that.
No, this is like a multi-body wave function, right? Because this is a tensor product of a bunch of different sides, right? So I can easily have them. So like
But you've got a. That's exactly how I write down a single particle ansatz, a tensor product of single particle states.
but I can put in a particle here and I can put in a particle here, right?
Yeah.
So this you can also think about this like as discretizing a field theory, right? That each is a point in space, and
It's all incidental for almost. So you have a product ansatz. Just do, the particle operator expansion of the quantum field. It's exactly what you do with the product and ansatz. So. But I guess it's more general because that's a matrix. Is that the point here?
oh, sorry, this is not a pure. This is not a product state, right? Because we have extra summation here, so it's a sum of product states.
That's incidental to this.
Yeah, so it's a full matrix.
Product state that use as a basis.
Yeah, use the matrix, and the basic structure then gives you a sum of those, and you get something that is not a product state.
But it looks, I don't see what's the point. It's silly.
Right, maybe we can talk about that at the end, because I want to get back to the gauge theory. Because now we have this ansatz, and then you can ask, well, where does the gauge theory live, or gauge field live? So in the first set I was talking about, there's no gauge field because we gauge fixed it, so we only have the matter, which lives on the physical links. And in the second ansatz, we have both the gauge field and the matter, so you kind of have to have both of them on the physical links. So here I said that the matter lives on the odd links and the gauge field lives on the even links, and then you have to tweak your ansatz such that it actually solves Gauss law. So this is what people usually do. And what I want to try to do is I want to take like a hint from this initial drawing I made where we had the gauge fields on links and matter on sites. And then that kind of lends you to think about thinking about the virtual bonds as the gauge field, and then just having matter on the physical links.
But when you say gauge field, you might that you're going to keep say external gauge field, but the name of gauge field is epsilon, right?
Yeah, this is 1+1D, so there's no dynamic gauge field. That's
So,
true.
so is this way it's like external, right? No, because I mean I can put some electric field, but it will be
So what will happen here is they only get the gauge field that is due to some charges. Like so in that sense, the external gauge field is turned off, if you want to say it like that. So yeah, if my system is in one big plate capacitor, then I turn off the plate capacitor. Right. So this is of course a nice picture, but it's not enough for the picture. It kind of has to do what you want it to do. So this needs to solve some kind of Gauss law to actually be a valid state. And that's what I'm going to try to argue for now. And what we need is actually something that already exists, which are symmetric MPSs. So these are matrix product states that are designed to just diagonalize some global symmetries. So you want to make a wave function that transform covariantly under some global symmetry you have. And the way that people do that is that say, well, one way to get a global thing that transforms correctly is just to say that every single MPS tensor transforms correctly. So we choose all the MPS tensors to be group invariants, or more generally, coordinate coefficients, and then we try to make our MPS. So an example of a abelian one with U1 quantum numbers is that I take some physical states with some U1 charges here, and then I think about what are the allowed things we can put on the virtual links. So to put zero charge here, then because nothing's coming in, I have to put zero here, and then when I fuse zero and -1, then I have to get -1, and so forth, and then I get zero, and then you get like overall a singlet. So this is just a product state here, because like the bond dimension is things we want. But this also extends to non-abelian symmetries. So here I take it to 2, and then if I put all the matter to be spin half, then for the first one, here I can only put spin half because nothing's coming in, but then when I fuse a half and half, then I get either 1 or 0. And I go on and I could go either up to 3 halves or down to 1 half, and then in the end, I actually don't terminate it to be 0. I have an open index. So this would be an MPS for a charge state that's transforming the spin 1 representation. Of course, we don't really want that for doing gauge theories because we want gauge singlets, but this framework accommodates that. But what's totally obvious now is that to construct a valid symmetric MPS, we actually have to solve a Gauss law for every single MPS tensor. So in that sense, the MPS already does gauge theory for you in this sense. And I said this, of course, is only like with one dimension 1. There's only one thing on every link, but you can upgrade this to be like a full fat MPS by saying that you can have the same rep occurring multiple times, which is what I'm trying to indicate here with this dashed line. And then furthermore, you can also say that multiple representations can appear on these legs, so some of that as well, and you can make it into something that actually has a higher bond dimension. And just to emphasize that the reason why you wanted to use this kind of technology in general is because the fusion rules of the EREPs highly constrain, like we just saw, what can happen with these MPS tensors. So you can make much larger systems and have a larger bond dimension. So for example, if you look at this tensor here, then this is, if we disregard the symmetry, then this is 4-dimensional space, this is a 2-dimensional space, and this is a 3-dimensional space. So that would be like 24 components. But if I think about the symmetry, I only have to keep track of one component. So this is much more efficient also, in addition to solving the Gauss law. Yeah.
Yeah, I figured. Not mind that you're gonna do this also.
Well, so it's not gonna like be a good approximation, but then you can like tune close to a critical point, and then you try to extrapolate and find information about the critical system. But of course, like with MPS, you can only ever have finite correlation, right? So you can't actually have a critical system.
Okay, and then what principles do you use to choose permutations to go involved?
Yeah, so this was supposed to be an example of a valid MPS.
But that's just valid based on.
Correct.
In the sum, what?
Yeah, so when you set this up on your computer, then you choose some initial representations, and then depending on what algorithm you use, for example, DMRG, then DMRG will ask the Hamiltonian, what representations do you need? And then it like can dynamically change it around, and you find whatever you need to well approximate your ground state. And then you like, of course, have some convergence criteria, some truncation criteria, so it doesn't balloon. But yeah.
So I thought the techniques for MPS with non-abelian global symmetries were projecting onto sort of more complicated representations with pretty efficient. But you're saying they're actually very fast. Is that right?
Well, so at least so I don't know how it stacks up for if you actually just do this as global symmetry, but we need, for example, to make this into if we want gauge singlets. So if we don't keep track of the non-abelian quantum numbers, then we have to do like penalty terms to project onto the singlet sector, and that's expensive. At least we find that. Then it's more efficient to do actually keep track of the non-abelian information. Good. So what I try to argue is that we have to understand the virtual links as the gauge theory states, but then I raise the question: how do you act with the electric field? Because usually the Hamiltonian acts on the physical links, but now we kind of have to act on the virtual ones, and so that doesn't really seem to fit with what you usually do. But what you usually do in MPOs is actually not in MPS, it's actually not to do this kind of contraction. What you do is you make a product representation of the Hamiltonian, where itself is written like a product like this. And then you do the contraction from left to right, because then you only have to keep track of free open indices rather than ordered system size indices. And from that point of view, it's quite natural to include these link operators. So you just say you do the normal thing, then you act on the link with the Casimir, and then you do the normal thing and you act on the link. And this sense, it's local, it's like on one side or one link. This is like to be contrasted with the other method I was talking about, where you get something that is on a bunch of different sites. And in particular, because it's only one link, it doesn't actually even enlarge the MPO virtual space of the free theory. Good. Great. So that was basically all the technology I want to introduce, and then I want to try to apply it. But before I do that, I want to just quickly recap what we did. So what I argued was that you could give the virtual links a physical interpretation of the electric field. And so you can use that to do actual computations, but you can also do it to include physics. So for example, in QD2, there's a parameter region where you have C-symmetry breaking. So that's a vacuum that has like positive electric field and one that has negative electric field. And by saying that the virtual links are the electric field, well, then you can say, if I choose positive representations on my virtual links, then my algorithm will actually converge into the positive electric field vacuum, and we're going to do it for the other vacuum as well. Also, in states where you have different flux tube sectors, for example, adjunct QCD, there are the different flux tube sectors are designated by the anality of the electric field. Well, if the electric field is the virtual links, then you just choose the correct anality on the virtual links, and then you get the flux tube sector you're wanting. Yeah, and as I showed you in the previous slide, it's really only like a small step away from the normal MPS algorithms. So you can implement this into like the normal DMRT routines and bumps for infinite systems, and yeah, basically most algorithms will work. It's not a big difference. And then from a point of view as somebody who has to actually put this on a computer, then it's quite nice because you can abstract away all this gauge theory headaches of how to solve the Gauss law, fuse E-reps and everything into this black box, which is just these symmetric MPSs that other people have already thought about. And so in particular, you can leverage the codes that's already available and the algorithms. So a bunch of codes available publicly. So a few of them are 10 pi and 9 tenses. They do a billion quantum numbers. So if you want to do QD kind of theories, then you can do that, or set gauge theories. And then at least I know of two codes that does non-abelian things. So QSpace and NPS-Kit. And the one we've been using is NPS-Kit. So we've taken their code and then we've stuck on these extra link operators. Right. And then maybe one caveat I want to mention is that just manipulating, like doing the contractions of these symmetric MPSs, that will require 6J symbols or F symbols for that group. So of course that's not a problem for abelian groups, it's just trivial, and for SU2 it's known in closed form, but for SUN or high number of colors it gets increasingly hard because you have to find them numerically. But we can do like 3 and 4 colors, and I think Ross tomorrow will show some results with that. And maybe the things I find most nice about this is that you get translation invariance. And so we can try to use some of these algorithms that comes from condensed matter, where you use an infinite system. The lattice is infinite to begin with. And that's what I'm going to talk about in the rest talk. Right. So how do you make an infinite state? Well, you just take your MPS and then you just continue forever. So you make it periodic. So this is the simplest example where you just have a period 1. So you take the same tense and repeat it over and over and again. But you can also have like period 2, have A1, A2, A1, A2, and go on. And so that gives you an ansatz for infinite multiplied wave function. And then people have thought about how to solve for the ground state. And like one of the most popular algorithms is this Baum's algorithm, which also dynamically adapts what the virtual links are. So it automatically chooses what electric field variables you have. But what I really want to show you is how to find bound states, which you can do with this force particle ansatz, where you choose one of your tenses to be some disturbance, and that's a new variable parameter you have, and then you can make it into a plane wave, and then there's some ansatz for bound state, which you can then try to apply to the system. And the system I have in mind is the SUN gauge theory with the fundamental matter, because usually I do adjunct QCD, and so to show that this is more general, that I'm doing a fundamental matter here. So it has long history, it's been studied both the large NC and also the finite NC, where you have to do some more elaborate numerics. And there are also some results in bosonization. In particular, you can develop a T for energies much smaller than a coupling, and for zero quark mass, it comes out to be some compact scalar. And as you turn on a quark mass, you get some Søgaard potential with some mass scale that depends on the number of colors. And so what I want to show you is two colors where the mass scale comes out to be 2 into 2/3. And Søgaard also tells you that you're going to have 4 particles, you're going to have 2 kinks and 2 breathers. So for this value of the radius, you get that the kinks actually degenerate with a breather, and then you have a heavier breather. So you get like a triplet and a singlet, where the ratio of masses is √3. And this triplet you can actually understand as some extended flavor symmetry, because usually for generic NC, you have just the baryon phase you can put. But for 2 colors, the fundamental is pseudo-real, and so you can actually make this kind of SU2 symmetry where you right multiply on this this 2x2 matrix, and the diagonal is this SU1 we had before, but then you get a full SU2 worth of symmetry. And so you get this triplet. Right. So to put it on lattice, we just take the normal complex staggered fermions. So this looks exactly like the Swinger model, if you've seen that before, other than now L and U means the SU2 quantities. And one thing you need to input is like what is the local Hilbert space, and you can work that out. It's of course 4-dimensional because it's 2 equation operators, but it breaks up into some SU2 representations. Yeah, I'm just going a little fast to be done within time. But this lattice model also has some of this extended flavor symmetry, which actually mixes with the translation, which is something that often happens with these staggered fermions. And then you can figure out the branching rule of the triplet we saw before. It goes to singlet and doublet on the lattice for finite A. And that is something we can see on the lattice. If I run this quasi-parallel ansatz to find the bound states, then these are the lowest free, and there's a doublet here, and a singlet here. And as I take A to 0, they nicely merge, and I get a triplet. So if I do that for some mass, if I do that for all different kind of masses, then I get these 2 lines. So this is a triplet, that points on top of each other, and a singlet. And if I try to fit some points for some power law, then I get some power which is pretty close to 2/3. And if I furthermore take this fit scaled up by √3, then I get this all line, which also neatly aligns with the singlet. And then also, well, I didn't have much chance to say it. There have also been some earlier studies for this 2-color model with some finite system G, where they also get this triplet, and you see their data points also roughly match ours. Right. Yeah, so this was basically what I wanted to say. So what I hopefully came across is that MPSs are basically gauge theory states in 1+1 dimension. And this point of view allowed me to introduce these new kind of matrix product operators that basically allows you to implement any gauge theory, well, with the caveat that you need 6 symbols, so that of course restricts you a bit. And then I tried to apply this kind of machinery to 2-color SU and gauge theory and compare to these personalization results and found agreement with the low-lying states. And this kind of program can be pushed even further because I already showed you these particle ansatz, which is kind of like a wave, a plane wave of a bound state traveling one direction. But in condensed matter, we actually studied how you stitch together 2 of these things, such that you can get the eigenstate corresponding to 2 scattering plane waves, and then in a quite explicit way, you can try to read off what it is matrix. So that's like, well, that's kind of a static way of extracting the S matrix. But then you can also, of course, do real-time dynamics. And then what's maybe more interesting is that some of these ideas of using the virtual links as gauge fields, well, you can lift them into higher dimensions, and you can try to do 2+1D systems. But that's of course much harder, like even the for like normal spin models. So like in Bennett's meta literature, it's much less developed. Like how do you actually do technical work with some on 2-dimensional lattice? But that could be interesting if you would be able to do that. Yeah. Yeah. Right.
In the infinite length discussion, how do you treat the asymptotic? You talk about the kinks, so there are different ground states, right? So
Right. So the kink here is like of a complex scalar, right? So it doesn't actually give you different different topics, but you can actually. So there's a small extension to this ansatz here, where here I took the same ground state on both sides, but you can also, like there's been like studies of the Søgaard model where you take one ground state here, some defect, then another ground state here, so you can actually solve for the kinks using this kind of ansatz also. Yeah. Yeah. No. So where I only have the same tensor repeating over and over again, that's just a vacuum. And to get something that is representative of a bound particle or like some asymptotic state, I say that is kind of like I do some local disturbance at one point of the lattice, and then it's smeared into like a plane wave. But also, like I get to grade it with the momentum, right? So I can actually extract like the full dispersion. So I have some.
So you're breaking something like the particle out. Right?
Yeah. With well, why would I miss them? Oh, well, so of course it does. If it's something like that's extended, well, if it's like a kink, then I wouldn't see it because it's like different. But like if so, even though this ansatz, okay, now I have to go back again. This ansatz, you only change the tensor here. Then due to the fact that it's actually a matrix product, then the influence is just not just living at one side. Like the influence like spreads out, and you like the larger you take a bond dimension, the larger like area you can influence.
But is it possible there are particles there that are not captured by that ansatz, or would you need like a finite length that are just one side modification?
So I guess it's possible that the things that cannot be captured, but what I just want to emphasize is that this is not just a modification on this side.
Yeah.
Yeah.
Long stream of states, blah blah blah, and the state will be very large.
Right. Yeah. Okay. Yeah. But then I guess you could mix it.
You also could want to bring translation variance, right? So you probably want the B matrix to be the same for all sides of the time.
Yeah. But if it really has to be like a finite size and continuum limit, then you also would have to like just make your ansatz much bigger as you're taking the lattice basically smaller, right? Yeah.
So in 2+1 dimensions, this is actually sort of solved this.
Yeah. So exactly that's what I had in mind. But it's much harder in 2 dimensions because like what basically enables you to do anything with MPS is that in fact you can contract horizontally. But when you have a 2-dimensional network, then like both directions are infinite, so there's no easy direction, and so that makes everything more complicated. But people have indeed done stuff like the corner transfer matrix, renormalization group, and stuff like that, and that's what I hope to be able to do something with.
About the product, like say for integrable model, like say side button or just where there's also just kick or kind of this. There is also solitons are fermions, for example, so you have quadratic and harmonic stuff. So in this, and the answer there is no, right? So I'm not sure that it could be applied the method to those integrable three.
Sorry, in that there's no what?
Oh, you have this integrable three.
Yeah.
Okay, and I wonder whether you can, and there you have this fermion boson duality as the same theory. There and fermions are solitons of your original formulation, and I wonder whether the methods of this matrix closure could be applied to this integrable mode.
Yeah, so people have done that, but what I do everything with fermions, right? And then from like the theory side of things, I know people have shown that this is effectively described by some Søgaard model, but like what I put on the computer is fermion, and then like you get out the bound state that would correspond to some Søgaard.
But it is this way, fermionic description and bosonic description of the same mode.
Yeah.
And in this way you can see kind of quantum probably in your message, you can see how one is related to another, right?
Well, I don't think you can like make a very explicit map of how the, like how to map the two things.
Yeah.
Well, that's not quite true, right? Because like you have the like Jordan-Wigner transformation, that's post-ionization, right? On the lattice. Yeah. Okay. Oh, yeah. That was what I was trying to say, yeah. The Thangon is just like some inputs from some paper in the 80s. It's not like something I did. I just had the stack of fermions and then I ran the algorithm and out came the masses corresponding to an effective theory that is Thangon model.
So if we continue, we know that 2D UCD has some non-invertible symmetry. So you're just looking at the quadratic theory without four paragraph. Is it possible to incorporate those?
Well, so we're very interested in doing this kind of thing, but we don't really know. So at the moment, like we're kind of trying to push what we can do with adjoint theory at the master's point where these are present. And on the lattice, there's some like anomaly structure that guarantees some of the vacuum degeneracy, but the non-vertical symmetry is supposed to give you even more. And so we're currently trying to do stuff where we do like 4 colors, where you're supposed to get more vacuous than the lattice model is supposed to give you by anomalies. And so we hope that by like looking at what are the solutions where we like numerically find that in the continuum limit outcomes to degenerate vacua, which are guarantees by non-variable symmetry, maybe that will give you a hint as to how to do this. But
you can also do it with smaller colors, but not add.
right, yeah. You think about this as 5 in which also fits into this the 5 issue 2.
We can talk about that.
Yeah, but that's something we're interested in doing also. Right, but yeah, the point is that this is like pretty generic and particularly can also do that theory.
But you don't know how to incorporate the symmetry structure of the figure yet.
Well, so yeah, no, I don't know how to input the non-variable symmetry. It's also not clear whether they are there, like for final lattice spacing, right? It could be that they just
Depends whether the examination respects some.
Yeah, exactly.
That's what I'm asking, like maybe he can put into his ansatz that he wants to hit the near just.
Oh, I see.
Yeah, you can maybe control the 4 fermion from the
Otherwise, standard, usually in that case, you did feel some kind of doesn't.
Right. Yeah, exactly. So, but I wonder if you can choose by choosing answers, which recommendation.
Right. Well, that would be very neat if we could do that, and we'd be very interested in, but as of now, we don't know how to do this. Okay, thank you again, Sven. Yeah.